Hello, everybody, and welcome to Chapter 4, where we're going to talk about working memory. Working memory is comprised of several different things. We're going to get into them one by one. As always, we're following along in the textbook, and I am using the in-class version of the PowerPoint as opposed to the full chapter version that you may have access to. So here we go. By way of introduction, we are talking about short-term memory and working memory, and that they refer to the same cognitive process or two different names for it. The idea of short-term memory has been updated, and because of the updates and the kind of qualities that research has uncovered, it goes from short-term memory, which is basically time-bound, to working memory is more of a functional, mechanical way that memory works, that the short term or the shorter term version of memory works as opposed to long term. Right. So where does this come from? Classically, we had the difference between short term and long term memory. Short term was said to be very brief, on the order of seconds long, which is a lot shorter than most people think. People think that, short-term memory, I remember what I ate yesterday for lunch, that's short-term memory. That's technically long-term memory. Short-term memory is even shorter than that. Long-term memory then is the memory that you have that gets stored for long periods of time. It can be semantic or episodic. It can be procedural memory. All different kinds of memory get stored in working memory, and that's also memory with reference to sensation. So you can remember what it felt like to put your hand on a hot stove. So we have sensory memory as well. George Miller comes up with the magical number 7, which is a good bit of research. It's based on the idea that people can remember about 7 bits of information. That's 7 plus or minus 2 generally. And that can also include time, so about 7 seconds worth of information, plus or minus 2. The research was interesting on that and determining exactly why that number 7 is so important, which is why it became the magical number 7. We'll talk a little bit about chunking in different chapters too as a memory mechanism, but you can remember 7 different numbers, like a phone number, for example. And if you've never heard the number before, you might have a harder time memorizing it. But if it's a number that you're familiar with, like a local phone number to where you are, and maybe a campus phone number, like if you're going to dial ITS from off campus, you'll dial 749-7666, and that would be one of the ways that you could chunk by having the first 3 numbers and the last 4 numbers, especially if you're familiar with phone numbers on campus. So if you know that 749 is the usual way that phone numbers start, and if you already know that the ITS phone number is 7666, you may or may not know that. But if you know those 2 little bits of information, all of a sudden you're not memorizing 7 different numbers for the phone number. You're memorizing 2 chunks. And that means that you've only used 2 of the 7 plus or minus 2 bits of information that Miller suggests in the magical number 7. Excuse me. The same thing works with like addresses. So if you need to memorize somebody's street address and they live in the same city as you, you don't have to additionally memorize the name of the city, the name of the state, and the zip code. All you have to do is memorize their street address, and that's good enough because you can implant the other information into it based on what your memory already has stored as a chunk. What's interesting about Miller's research is that he recognized that there is a way that people innately take in information and then chunk it. So it's not that you have to rehearse the chunk necessarily. We recognize it automatically, and through rehearsal, and sometimes it's unconscious rehearsal, just seeing things over and over again, that you can develop these ways of chunking information, and they're kind of intuitive to the individual and specific to the individual based on the context of the information that they're taking in. Now, another bit of research about the same time is the Brown-Peterson and Peterson technique, where we start talking about rehearsal strategies. And the deal is that if you try to memorize something and then you're distracted, you may or may not be able to recall the things that you were tasked with memorizing. This is actually one of the ways that we test for, briefly, cognition in therapeutic settings. We'll see if people are oriented to person, place, and time, and one of the things that we also check is, do they have short-term memory that's intact? Where we'll ask them to memorize 3 things. I use the same 3 things: apple, sidewalk, penny. And then we use a distraction task, like starting at the number 92, count backwards by 3s until I ask you to stop. And then I ask them again, after about a minute or so of them counting backwards, what were those 3 things that I asked you? And what ends up happening is that people who have reasonably intact cognitive processes will be able to recall those things, even if they have to struggle for a second to think of it. What that does is it tests to see if people have reasonably intact short-term memory. If they're able to rehearse those things, then that kind of defeats it. So we have a distraction task. Rehearsal is the way that we process information in an intentional way, practice, let's say, so that you can memorize it. So if we can interfere with their ability to memorize the material, then we can test a short-term memory. Because once you start rehearsing material, then it starts to get processed into long-term memory. So that was one of the first bits of research and an actual process to test on a typical scale. You don't have to be in a laboratory setting, but on a typical scale, we can do a good job of testing the short-term memory for an individual. And this is one of the cards that you might see for the Brown-Peterson technique. So it's modified for use in classroom settings just to demonstrate. But essentially what would happen is you would ask people, or the way that I would use this is that you would ask people to memorize the 3 things and, whatever, number 2. They have to remember the words sober, persuade, and content, or content. I guess they should probably choose a different word if it has a homophone. And then you ask them to start at the number that is listed, so it would be 254, and then ask them to count backwards by 3s as far as they can in about 20 seconds. Right? Now, remember, the goal is not that they do the math right. As a matter of fact, if they don't do it right, then they're focusing on the math and being wrong more than they are the things that you're asking them to memorize. So it actually works out quite well to use big numbers for people who are kind of math phobic. That way they don't actually rehearse something. Remember, this is to get them from rehearsing and practicing the words that they're supposed to remember so that we can test out the short-term memory processes. And what's interesting is if you ran somebody through multiple trials of the Brown-Peterson technique, this one here, what would happen is that after the first trial, people were pretty good at recalling information, so they recalled a lot of the words, 80% of the time. And then what happened was that after successive trials, there would be a lot less recall over time. And the likely culprit here is interference, meaning that there are other things that they're trying to remember, and it leads to their inability to remember what's happening or remember the words that they were supposed to. A natural segue into the serial position effect is the Brown-Peterson technique because it talks about remembering things in a list. And we may have talked about this earlier, but the idea of the serial position effect is based on the idea that we have a hard time remembering long lists of things that exceed that 7 plus or minus 2. And when it comes to what we remember, we found that we tend to remember the first things in the list and the last things in the list. So the serial position effect is composed of 2 different things, the recency effect and the primacy effect. Now, the recency effect suggests that we remember things that we heard last in a list. So imagine if you're going to the grocery store and you have a list of 25 things, and oops, you dropped your list in the parking lot, but you've looked at it a few times, so you kind of know what's on there. The recency effect says that you're probably going to be able to remember the last several things on the list. The primacy effect suggests that you're probably going to be able to remember the first several things on the list. However, the things in the middle of the list, you're probably going to forget at a higher rate than those not in that part of the list. So the first few things and last few things. So if there's a practical application here, maybe if you have a list of things and you need to remember them, put the things that are most important at the beginning and the end, and things in the middle can be things that if you forget about them, they're not so critical. And this is a demonstration of what the serial position effect might look like in chart form, where if you have a list that has 20 items or so, the probability of recalling each item is listed here. So there's a sharp decline all the way to the 7th item in the list, and then there's a kind of a lull. Then it peaks back up at 16th or so. So you have about a half a chance of picking up the first 5 and the last 5 or so, and then the middle 10 or so get lost in the serial position effect. So we see a primacy effect at the beginning, and then a recency effect at the end, and then the middle is where we see that certain dip toward the end or toward the middle, where we are more likely to forget things than to remember them. Okay, so one of the kind of quirky things or tricky things about memory is this idea called the release from proactive interference. And it is based on the idea that when things are similar to each other in terms of what they mean, so semantically, then we can have a hard time remembering new things, because if they are similar in category, then they interfere with each other. So if I asked you to remember 5 fruits, and then I ask you to remember 10 more fruits, and then I asked you name a fruit that you heard in the first list, you might get a little bit confused because, I can't remember which one was in the first list because the 10 that came after it are similar in category, and I can't separate out which ones those are. So we have what's called proactive interference in there, where the first information interferes with the information that you just learned. So it can be problematic for lots of different things, but just for the sake of describing it, we're going to limit it to talking about something mundane like fruits and vegetables and things like that. There is a variation on the Brown-Peterson and Peterson task for semantic similarity in terms of being able to remember things. And the way that this worked was that people were asked to memorize lists of things depending on what category they belonged to. So there was a group of people that were going to memorize fruits, some were going to memorize vegetables, some were going to memorize flowers, some were going to memorize meats, and then one group was going to remember occupations. And it's key that they remembered occupations because occupations are unlike the other 4 categories: meats, flowers, vegetables, fruits. And what happened was that for the first 3 trials, each group was asked to remember the thing that was categorically similar. So if the people were in the meat group, then they had to remember meats. If the people were in the flower group, they remembered flowers. Occupation, remembered occupations. And they did that for the first 3 trials. And what happened was that there was some interference that happened, as you can see in this chart, in the first 3 trials. So each group had to remember some things, no problem, because it was their first time, no interference. But in the second trial, remembering new things was interfered with by having remembered or having learned the first trial information. And then in the third trial, there's even more interference, because not only were they trying to remember these 3 things, they were also trying to not get interfered with based on the second and first trials. So the first and second trials were interfering with learning at the third trial. Well, on the 4th trial, each group saw a list of fruits. And what happened was this: the people in the fruit group had predictable interference because they had 3 previous trials of learning fruits, and they had a hard time remembering the 3 fruits from the new trial. Vegetables were also impacted by it, because even though they weren't learning vegetables, fruits are semantically similar to vegetables, and same as flowers and meats. Vegetables and fruits and flowers and meats are all things that grow. They're things that are edible typically. So there was a lot of overlap there. Although there was some rebound from flowers and meats because meats and flowers do have enough differences from fruits in order for it to have some kind of release from that interference. But look at the occupation group. The occupations group on that last trial also memorized names of fruits, and they had a nearly complete rebound to pre-trial memory, which means that they didn't have the same interference as the other four groups did because the occupation category was not semantically linked to the new fruit that they were trying to now memorize. So they had what's called release from proactive interference. So when you find that that you're having a hard time memorizing things because you're getting confused about things that you've learned prior, try to switch it up a little bit, learn in a different way, or maybe recategorize something so that you can think of it in a different way. So if you're going to the grocery store, instead of thinking, man, I have to get all these things, all these different kinds of pastas, maybe think, okay, I'm going to make these several dishes. Now I can remember what pastas I need rather than just remembering a list of pastas. Because if you're going to make spaghetti, you probably don't want to get rotini, although you could make, a rotini and pasta sauce. But if you call it spaghetti, then you don't have to think, oh, I need, or then you're not going to get confused thinking that you need rotini. Or if you think, I need noodles, but crap, what kind of noodles was it? Oh, that's right, I was going to make lasagna, so I need lasagna noodles. So you can think about recategorizing things so that you can release yourself from proactive interference. Now let's shift gears a little bit. It's really not shifting, more of a flow, but we're talking about the Atkinson-Shiffrin model. And this model has kind of come and gone in terms of how we conceptualize cognition and our memory approach, because there's a model that talks about working memory. So the Atkinson-Shiffrin model is about information processing, just in terms of whether or not something gets stored in long-term memory. So the idea behind it was that your mental processes function like a computer, where there's this kind of like serial input. Things go in, they get categorized, they get stored, and then they get memorized. Okay. And then the other part of it was that, as I alluded to, the serial idea is that information does go through stages, but it's one step at a time. And spoiler alert, we know that that's really not the case, but that's the working model that we're talking about now in terms of the evolution of working memory. And the model kind of looked like this. So there's some kind of external input, like you're listening to a list of words to memorize. So you have the external input. In this case, it's audition. You have auditory input. It goes into sensory memory. And if it goes into sensory memory and that's all, and you really don't process it, it gets lost from sensory memory. This happens constantly. If you're at the KC eating, or if you're eating out at a restaurant and you hear all the background noise, you're not processing it. It's going into your ears. Your ears are resonating, right? There's transduction in your ear that's happening as a result of the information, of the stimulus that's coming in terms of the sound wave, but you're not actually processing it. So that gets lost from sensory memory right away. Then there's short-term memory, or what we have been calling it synonymously, working memory. And in working memory, you can rehearse the information if you can, and then it has a chance to go into long-term memory. But if you can't rehearse it and you don't need it and you haven't memorized it in any other way, then it gets lost from short-term memory. So thinking of like a phone number that you're trying to remember. You remember it long enough to dial it, and then as soon as you dial it, it goes away and it gets lost from short-term memory. And you might be able to like fumble back through to get it back, maybe by trying to remember what the pattern was or something, but generally it's gone. You don't get to have it back. Now, if you are able to process information, it can go into long-term memory, and that goes through rehearsal. And there is this kind of cycle that happens between long-term and short-term memory, because each time you access a long-term memory, it goes back into short-term memory as a way for you to like recite something. So if I'm trying to think of a word to say, I have to think of the word. It goes into my short-term memory long enough for my mind to think, okay, how do I form this with my lips? How do I co-articulate this word? And then I say it. And then all of a sudden, I've accessed my short-term memory. But what's kind of cool is that by saying it, I'm actually rehearsing it because I'm using motor planning in order to do that. So I'm kind of coordinating the way that my mouth works as a way to rehearse what the word is, which is why when you have a tip of the tongue phenomenon, you're trying to think of the word and you can't quite get it, you kind of like start to mouth it because motor planning facilitates memory. So we have this kind of working memory cycle that integrates different systems in the body. Over time, the Atkinson-Shiffrin model has fallen out of favor because things like sensory memory are part of perception, and perception tends to be integrated in the memory systems more theoretically and from a research perspective in a more integrative way than does the sensory memory. So we have started to think, okay, there's perception that happens. You have a sensation, it goes in, but it gets processed in the in the perceptual parts of the brain, depending on what the sense is. Each sense kind of gets processed in a different place, whether it's sound or taste or smell or whatever. So each part of the brain can then use that information to store it as a type of sensory memory, but it integrates in different parts of the brain. For example, when you think of a smell, you can often think of the context that goes with it. So there's some kind of memory in there. There's an episodic memory that happens in there. And also there's an olfactory sense. So there's a sensory or a smell, an olfactory sensation that we can perceive almost like if you think of smelling something like a Christmas tree, it's like you can almost smell it, but then it's accompanied by a memory. So we know it's not just simply there's a sensory memory, but it's integrated deeply and quickly to the point that we really don't think that it's so much just sensory memory gets stored in a sensory memory bank. It gets inputted and integrated quickly. Okay. So one thing that we drew from the Atkinson-Shiffrin model was that even though there is like this desire to be distinct and to talk about, there's short-term memory and long-term memory, we want to separate them out and treat them differently so that we can talk about them differently. The reality is that everything is so integrated that we can't just say that there is short-term and long-term memory and they kind of like communicate, but they're not overlapping. That's not really the case. There's a lot of overlap between these two systems, and that's why we have this idea called working memory, which gets a little bit more complex, but certainly something that you can sink your teeth into. Moving away from the Atkinson-Shiffrin model, which is not to say that it wasn't important, it's just that there was advances that replaced it, but it was still foundational in some understanding of short-term memory processing. We moved to working memory. So working memory is kind of like the way that we process information from a short-term perspective, but on steroids. It's more of an active process that leverages different modules in the brain. So the short-term memory is not just a place where things go, it's an active place where things get processed. And the reason why we call it working memory is because it is not just we memorize things and it gets shuffled off into a new part of the brain. It gets used and it gets rehearsed a little bit. And it uses different parts of the brain to inform what the new thing is. So we have some top-down influences on our working memory too, so we can contextualize what we are taking in through our working memory. So a quick demonstration, you can multiply some of these in your head within a reason. 7 times 9, you can multiply that in your head and get 63. But then you do 9 times 74, or 74 times 9. That gets a little bit trickier. There are some strategies that you can use to do that. You can kind of use nice numbers is what they're called, and do something like, let's see, it's actually 74 times 10 minus 74, so it's 740 minus 74, and you can math that out, or you can kind of like replicate a multiplication process in your head and say that it's 4 times 9 is 36, and 9 times 7 is 63, so it's, let's see, and you kind of math it out in your head that way. But once you get down to 74 times 96, things really go off the rails because now you have to keep too much information in your mind at once to try to make the math work. It's enough to try to do 74 times 9 in your head and kind of work it out mentally because you run out of space to do it there in short-term memory. But 74 times 96 really puts the pressure on most people, and it's usually not something that you can do within reason. Even if you tried some tricky things like saying well, 74 is close to 75, so if I just say that it's 75% of 96 and you divide 96 by 3 or by 4 and then multiply it by 3 and then take away one of those. Okay, so you could try to think of different ways to do it, but by the time you start getting into the rigmarole of doing it, it's impossible to keep track of it all in short-term memory. Similarly, another demonstration, you can read some sentences, and it's not about math, it's just about literacy, and you could understand what was going on in the sentence, in the first one especially. The repairman departed, no problem. The librarian that the secretary met departed. So adding in that extra clause that the secretary met makes things a little bit tricky, but we can still keep track of it. The salesman that the doctor that the nurse despised met departed. Even though when you say it like that, it doesn't make a lot of sense. When you parse it out, it does make sense. The whole sentence is about the salesman departed. Then everything else kind of identifies other information about it. For example, that the nurse despised, okay? That the nurse despised is talking about the doctor. So the salesperson that the doctor met departed. That the nurse despised modifies the doctor. The salesperson that the nurse despised met departed. Now, that may or may not have clarified anything for you, but once you start to talk about what the sentence means and give some inflection in there, it starts to get teased out a little bit. But the reason why that's tricky for us is because by the time we take all the information in and consider all the modifiers, the grammar and syntax has gotten funky. It's not incorrect, it's just funky compared to what we were used to seeing, and that makes it tricky for us to keep track of because it violates some kind of order and clarification. This is a nasty sentence that, while technically is true, wouldn't get you anywhere in formal writing because it needs to be revised, even if it's correct. So working memory, just by these demonstrations, includes several things. The working memory goes from the initial thing that we are trying to consider mentally, so some kind of stimulus, whether it's a thought, trying to memorize something, whether it's something that we see or hear or think or whatever. It has to go through several different stations, and the first station is the central executive. Maybe I shouldn't say the first. It is the first listed, but I'm not saying that has priority. But in this model, the first one that comes up is the central executive, which kind of determines what to do with the information, and it kind of cycles back around the different parts. And then we have three kind of sub-parts of this model called the visual spatial sketchpad, the episodic buffer, and the phonological loop. And those communicate back to the central executive, which tries to coordinate them in a way that that makes whatever you're looking at or thinking about makes sense. And it's almost like a meta strategy, the central executive. It kind of says, okay, how can we solve this problem, especially in the case of a very complex sentence? And then the last is the long-term memory, which is where things go once they survive. Is that the right word? Once they survive the visual spatial sketchpad, episodic buffer, and phonological loop. So this is kind of the diagram of what that looks like, kind of giving some order to it. Now, we do have limitations in working memory, and that's okay. That's a concession. Well, it's not really a concession. It's just the reality of the different specialty that the working memory has. So working memory is an active process. It's not just this thing that sits there and information kind of falls through it like a sieve. It does stuff with information. All the information that we know about the short-term memory that we learned from the prior model still apply. We still recognize that there are limits, like the magic number 7 plus or minus 2. and other aspects that are relevant to short-term memory from the Atkinson-Schriffran model. And all the information that we know about working memory and long-term memory are the same as what they have been, that it's limited. And we recognize that. So the phonological loop is, referring back to this, is one of the elements that interacts with the episodic buffer and visual spatial sketchpad in order to make sense of information. And it can process information relatively easily, and it's limited in the same way that other models have suggested. So the phonological loop is kind of this subvocalization, or this repetitive kind of voice inside your head, like when you're trying to memorize a phone number. When you memorize a phone number, you might just repeat it in your head over and over and over again. That's the phonological loop. Right? It's based on the sound. So you literally hear a voice inside of your head. And this also has an element related to it called subvocalization, which is what happens when you try to read something. So with subvocalization, you're reading a book and you kind of have a voice that reads along with you. The cool thing is that if we can turn off subvocalization, we can actually read faster. So it does get in the way. So our phonological loop, while helpful for rehearsal, gets in the way of fundamental processing. And we've also talked about subvocalization back in chapter 2, I believe. So this will be a little bit repetitive, but repetition is a good thing. So we can take a quick look at the Spreeder app, and I'll plug in the text that's in very small font right below it. So here at Spreeder.com, I've plugged in that short paragraph, and it's going to be at 300 words a minute, which is pretty modest. It's not terribly fast. We can read faster than this if the words weren't presented one at a time. So I'll push play, and you can kind of see how fast this goes. And at the end, I'll ask you a question and see if you notice. All right, that was a pretty modest reading pace, and what you might notice here is that as the words are popping up, you were saying them to yourself. That's that subvocalization. That's kind of the phonological loop that we use. I'm going to speed this up considerably, and I'm just going to make the jump right to 700. We'll do 900 words a minute, which is pretty quick, but I think that you can still read it, and we'll see if you notice anything different about that, except for that it's going faster. That's obvious. So we'll start this in 3, 2, 1. Okay, obviously a lot faster, but I am betting that you weren't able to subvocalize. You're probably able to pick up a lot of the words, if not all of them, and enough to get the gist, but you probably couldn't say any of the words in your head. You just kind of had to watch. And that's how you can turn off subvocalization, is by presenting these things so fast that you can't speak them. One of the rules of thumb about reading is that you can only read as fast as you can talk. And most people can't talk at 900 words a minute. Most people can't talk at 500 or 600 words a minute without significant strain. So the idea here is that if you can outpace your vocalization, then you can get it to shut down and you can read a little bit faster. And the phonological loop is part of that process. So with phonological loop, there's also some errors that can happen. One of them is with acoustic confusion. So acoustic confusion is a very interesting thing, and you can get confused by the way that words sound, or excuse me, the way that letters sound or phonemes sound. And that can confuse your ability to remember them. Some of the examples of letters that sound similar are C, T, D, G, V. and B. And to remember letters like that or to distinguish letters like that can be tricky because you get confused. You have to spend a lot of time trying to look for small distinctions in them. You have to use bottom-up processing to know what the letter might be based on context and things like that. You can't just rely on what it is. So we can have problems with processing, and that can lead to inability to rehearse information in an accurate way. Even when we see letters, they get converted to an acoustic code or a sound-based code when we're using the phonological loop. So even if something is visual, it gets presented in an auditory kind of way. So the phonological loop is that gateway working memory is the gateway. And we use the phonological loop during times of like self-instruction, during the process when we're trying to communicate with long-term memory. So it's not only I'm trying to remember a phone number, it's also, I needed to do this, this, and this. So you might repeat to yourself what you're trying to do in types of a procedure. So the phonological loop becomes really important when we are trying to not only just memorize things, but also when we're trying to do like self-instruction. It also helps us to learn new words in the first language. So when we're trying to remember or learn new information, like if you're trying to do like a Duolingo or something, sometimes what you'll do is you repeat that word and you might compare it to a word that you already know and try to draw a connection between it. And also when we are trying to produce new language, we'll use that phonological loop almost like we're preparing to say something. It's very curious, especially when we are listening to other people, that we will try to predict what they're going to say, and our phonological loop will start to be active as they're speaking, which is why when people are usually looking for a word to say, you're pretty good at helping them out because you can leverage that phonological loop. Okay. Other examples too, I'll leave those to the textbook. Now the Visual Spatial Sketchpad is interesting in that it requires imagery, so you have to be able to imagine something. And the Visual Spatial Sketchpad uses processes both the visual and spatial information. One of the best examples I've seen of the Visual Spatial Sketchpad is during spelling bees. And people who are in these like very competitive spelling bees, when they're trying to think of a word and they're trying to think of how to spell it, they will actually draw the word on their hand, which is an externalization of the Visual Spatial Sketchpad. Right? It allows people to see what the word looks like. You're not allowed to write it out, but you can draw it, and that enhances things because you can visually see it, and also you're doing motor planning. If you are drawing the shape of a word, and we've all done this before, where you're writing a word and you're like, that's misspelled. How do I know? I don't know. It didn't feel right. It didn't. There shouldn't have been that combination of letters. In the same way, when you're going to speak a word using the phonological loop as a driver, when you're planning a word and you can't quite get the right word, your phonological loop kind of has like a hiccup, and you can't just it's like you're mispronouncing the word even though you're like consciously trying to get it just right. In the same way, the Visual Spatial Sketchpad can be used in that kind of way to know if something is right or not. Also, you can use a Visual Spatial Sketchpad to retain an image of something, so you can kind of like keep it in this short storehouse to know if there is a difference between things. And we talked about that way back when we talked about change blindness, what is different about something. And we know something's different because we maintained an image or a picture of that image in our Visual Spatial Sketchpad and compared it mentally to the thing that we just saw to see if something was different. So it's not that something is flashing, it's that it is different than what our Visual Spatial Sketchpad held for that image in that moment. We also use it for tracking movement and things like that. We use it in video games and jigsaw puzzles and all kinds of other fun stuff. So there's lots of applications for the Visual Spatial Sketchpad, especially with regard to the spatial ability to being able to mentally rotate an image or something like that. Now we're going to come back to episodic buffer in just a moment, but let's skip over to the central executive and talk about some meaningful integration that happens at the cognitive level. And not, I don't mean cognitive just like in the term of like in the sense of like cognitive psychology, but like there is a purposeful cognitive conscious process that happens in the central executive sometimes. There's also some automatic stuff that happens, especially metacognitively. But the central executive is something that integrates information from the phonological loop, the visual spatial sketchpad, and the episodic buffer, which we'll talk about in just a minute. So remember, this is kind of our diagram, and the central executive talks in an integrative way with all three of these things, and it goes back and forth. So it's kind of like transduction, where we have, or transponding, where you have information that goes back and forth, and one influences the other. It plays a role in focusing attention, so you have to like think of what to focus on. That's part of the central executive. Maybe you've heard the term executive functioning, and that's about how we organize our thoughts and things like that, and how we integrate our feelings with our cognitions, and how we choose to solve a problem. That's kind of the same thing. From a prefrontal perspective, central executive tends to be more kind of theoretical rather than an actual place in the brain. But we do know that conscious cognitive processing happens in the frontal cortex, or the frontal lobe. So it's not completely distinct. Coordination is another big thing for the central executive, to coordinate how to memorize something or what to memorize. If something is semantically important, like if there's a word that you need to memorize that's important, or like a combination to your locker, the central executive will say, yes, we're going to memorize other numbers, but we have to know this one because it's more important than the others. So that's some of the things that your central executive might do. And by prioritizing, then it will also suppress irrelevant information. It's kind of the byproduct of prioritization, is that you suppress irrelevant information. Plus, we know that short term, that working memory is limited, so you can't pay attention to everything all at once. Right? So again, some of the things it does just by in a list form, plans and coordinates, but it doesn't store information. Just other parts of your working memory store the information. It just tells it how to store it. It's a supervisor. It talks about attention. It selects strategies. Lots of other stuff that it does even beyond this list. It's just a traffic cop. It wants to make sure everything's doing the right thing and as efficiently as it possibly can. Interestingly, though, daydreaming, a fun topic. We've all done it. I've done it. I may have done it during this lecture. I can't remember. Sometimes you don't know. But the idea of daydreaming is that you don't have sustained attention on a task and your attention drifts somewhere else. We've all done it. It's fine. No problem. We're humans. But there was a study by Teasdale that looked at the ability for us to map daydreaming and to dictate the limits of the central executive. For example, the central executive can get bored. Did you know about that? The central executive has finite resources, and the way that they tested this was by asking people to supply a random digit every so often. And in this case, they were looking at doing a random digit approximately a second, or basically as fast as they could. Not like super hyper fast, but they wanted to make sure that the individuals could select a meaningful number to them that would seem random. Well, what happened was that as they were doing this task, they got bored. And about every couple minutes or so, the participants were asked by the experimenters to write down what they were thinking, and sure enough, a lot of the people had been thinking about numbers, but they were also reporting other things other than numbers, like random daydreams and things like that. The tricky thing is that when people were reporting that they were thinking about like daydreaming and things like that, they were not actually saying random numbers. They were still saying numbers, but the numbers became a lot less random. And they did some math and statistical inferences to determine if some distribution has randomness to it. And they found that about every 90 to 120 seconds, people would lose the task of randomness and start to get less random, suggesting that the central executive was not able to maintain the focus as it was as the person was directed to do. It's worth comparing something that we learned about in Chapter 3, the executive attention network, to the central executive, because we've used a lot of the same terms for both. But the executive attention network has a lot more to do with the ability to carry out goal-directed, purposeful things, he says vaguely, behaviors, tasks, let's say, as compared to the central executive, which has more to do with directing where information goes once it gets into the working memory. So even though they both share some ideas in common, like coordination, there is a little bit of a difference. However, there is a strong correlation between the activity of both the central executive and the executive attention network. So there's a lot more research that needs to be done on that to figure out how those two things cooperate. But we recognize that they share enough in common to where it's worth drawing attention to that. Now, the third part of the model, the episodic buffer, which is listed kind of in the middle here. Again, these are not in any particular order. The episodic buffer is good at kind of storing information that comes from the phonological loop and the visual spatial sketchpad and the long-term memory. So what's kind of cool about it is that the episodic buffer can take in the new information and then network into long-term memory to determine how that information can be most effectively stored. So if we're reading a book by the same author, and we're reading a sentence and it's like, wow, this author has a really interesting writing style, the episodic buffer can say, yeah, we've seen it before. So we can compare it to that writing style and we can interpret a lot easier because we have a foundation for it. Same thing as if you've taken a class with a professor before. You kind of know from long-term memory how to navigate the class. So the episodic buffer can say, oh, you have that assignment to do. Remember, when you do assignments for this person, do it this way. So the episodic buffer can take information from the long-term memory. It can compare it to new information. It can share the information with the central executive, which can tell you then how to process the new information coming in, like, for example, about the assignment. So central executive can be that traffic cop that says, oh, we've seen this before. Here's how we did it last time successfully. And then it sends that information back to the short-term memory. And then as you go back to doing that assignment, it gets stored in the long-term memory, and you have new information to compare for next time. It's very helpful in that way. It does itself have limited capacity. Even though it draws from long-term memory, it doesn't have an infinite storage of long-term memory. So it is kind of that temporary memory system. If you're into computers, it is like the RAM of your brain, where it temporarily stores information from long-term, and then it kind of dumps it when it doesn't need it anymore. So that information still needs to be kept in long-term memory, which is kind of what happens if, like, let's say with the example with doing an assignment for the same professor. If you forgot how to do that, you did well on the assignment, or how to do it for that particular professor, even though you've done one before, that means that the method you used to do that assignment didn't get stored in long-term memory, or if it did, it failed out of long-term memory, because long-term memory isn't permanent either. Then what happens is that you don't have anything to draw on, so you're kind of having to reinvent the wheel. So your episodic buffer communicates with long-term memory to avoid having to reinvent the wheel. But again, it's limited, and it can only access information from long-term memory if it's indeed there. All right, we're going to call that good for Chapter 4. There's another section that you can feel free to read over, but we're not going to get into it during this lecture. We've gone over a whole lot right now, plus you're allowed to, read the book and stuff. So do that. As always, if you have any questions, please reach out. Otherwise, I look forward to seeing you in the course room.